Our next speaker is Harry Atwater from Caltech. He's a director and lead principal investigator of the Joint Center for Artificial Photosynthesis. He's also the Howard Hughes Professor and Professor of Applied Physics and Material Science at Caltech, as I mentioned. And he received his SB and SM degrees and PhD in electrical engineering from MIT. He served as director of the DOE Energy Frontier Research Center on light material interactions in solar energy conversion and of the Resnick Sustainability Institute. He's also the founder and chief technical advisor for two venture-backed photovoltaic companies in the area of high-efficiency, low-cost photovoltaics technology. And he is also editor-in-chief of ECS Photonics. Among the many awards that Professor Atwater has received, he is a fellow of MRS, and he's a member of the National Academy of Engineering. I'm not going to read them all. He delivered the MRS Kavli Lecture in Nanoscience in 2010, and early in his career, he received the NSF Presidential Young Investigator Award. So with that, let me introduce Professor Atwater, who is going to deliver a lecture on JCAP. Please.
Okay, thanks very much. And so what I'd like to do here is to set the stage to tell you about the recent events in JCAP and the renewal of JCAP and its direction in a second phase. So overall, I'm going to describe to you the mission and the phase one discoveries and accomplishments in JCAP, and talk about our charting our new directions in phase two. And then I'd like to tell you about a couple of areas. First of all, that is the accelerated materials discovery effort. That's really a key aspect of rapidly developing new materials and concepts for solar fuels generators, and also then tell you a little bit about the portfolio of efforts that we're undertaking to look at heterogeneous catalysis for CO2 reduction. So in that regard, we have two speakers who will be following me, Matt McDowell, who's going to talk about protective coatings for stabilizing high-efficiency semiconductors, which has been an important development for enabling stable, high-efficiency solar fuels generators. And also, Ian Sharp will talk to us about bringing components to solar fuels prototypes, looking at the interface engineering and integration challenges. And I also want to draw your attention to a couple of other presentations by Francis Houle, who's the Deputy Director for JCAP, on tomorrow morning on multi-component electrocatalytic systems for solar fuels generators, and by John Stevens on mathematical modeling. So developing a scalably manufacturable solar fuels generator is truly a grand challenge, and it's one that was set out originally by Melvin Calvin, who was one of the first to intone the scientific community to really focus on this area. He advised that it was time to actually build an artificial photosynthetic system and learn what works and what doesn't, and that really was the founding impetus of JCAP, to use inorganic electrochemical and photoelectrochemical concepts to develop artificial photosynthetic processes that could be as scalable and as selective as natural photosynthesis, but much more efficient. And to do this involves a complex interplay of reactions and materials. And notionally, this is one of the a schematic of one of JCAP's integrated prototypes, which involves a tandem Z-scheme semiconductor photoelectrode to which catalysts drive reactions for oxygen evolution and hydrogen evolution at the photoanode and photocathode, respectively. And as I'll describe in renewal, JCAP is going to be focused on the considerable challenge of hydrocarbon production from aqueous electrolytes, which involve a complex series of reactions generating many intermediates and products. And in order to accomplish this, over the last 5 years, JCAP has developed a scientific effort that has been defined by integrated prototype developments, which define the assemblies and processes that are required, which then in turn drive the materials discovery efforts that have been undertaken. And this has been something that's been taken full advantage of the tools and capabilities that we have at many of the national labs and partner institutions, including the Advanced Light Source, the Stanford Synchrotron Radiation Lab, the computing facilities, electron microscopy, and molecular foundry, among others. And this is an approach that has involved many disciplines, including light capture and conversion, both heterogeneous and molecular catalysis, development of new materials by high-throughput experimentation. I'll tell you about one example of that. Benchmarking of the efficacy and stability of catalysts, understanding the molecular and nanoscale interface processes and the membranes required to separate the fuel products in a solar fuels generator, all of which culminate in bringing together these different components in a scale-up and prototyping effort, which is tied together by a process, materials, and integration team. And when all of this comes together, we get a result like this, which is a recent development in JCAP of a greater than 10% efficient, stable, and unassisted solar-driven water splitting device, which is essentially a monolithic photoelectrochemical system that's depicted here, in which we have stably protected tandem junction photoabsorbers and earth-abundant electrocatalysts, and anion exchange membranes. And this is showing Eric Verluch and CX Zhang hard at work in the lab developing these structures. And this solar fuels generator is depicted here, shown in a membrane assembly here, coupling the active photoelectrode, which is integrated with catalysts and anion exchange membranes. When operated in an unassisted solar fuels generation mode, essentially produces a unity Faradaic yield of oxygen and hydrogen. You can see here the device operating here. If you look closely, you'll see bubbles generating on the surface of this photoanode solar fuels generator. And we're able to achieve current densities here, which over the course of time remain relatively stable and give rise to a solar to hydrogen efficiency in the range of 10%. I would note that effort on photoanode devices is also complemented by effort on photocathode devices, which have the capability to be scaled to large areas and have shown also greater than 10% solar to hydrogen efficiency and stability over time, largely thanks to the advances in protective coatings that Matt McDowell will tell us about shortly. Over the last 5 years, JCAP has been focused on water splitting as an objective, as essentially a vehicle for driving the knowledge base, expansion of the knowledge base for solar fuels generators. And that has involved many challenges. Among them is the development of stable and efficient OER catalysts. And in the course of this, one of the contributions that JCAP and many others in the community have made is to really help define what the configuration and what the device level aspects of a solar fuels generator entail. And that's involved a increase in the scientific complexity of the overall assembly. And in renewal, JCAP is going to be focused very in a more concentrated fashion on many of the processes associated with CO2 reduction. And in so doing, we'll take a step back, at least initially, in the level of device integration and really focus on the component elements, membrane electrode assemblies, integration of catalysts onto electrodes, and really understanding how we can address the considerable scientific challenges associated with this really exciting problem of CO2 reduction. So importantly, JCAP is going to be focused on the electrochemical transformations associated with CO2 reduction, and of course also the corresponding oxygen evolution reaction, which paired together with CO2 reduction constitute the component processes required for an integrated CO2 photoelectrolyzer. Of course, there are many other challenges to finally being able to close the carbon fuel cycle with CO2 either at concentrated or atmospheric streams, including capture and concentration. That's outside the scope of our effort. Of course, many efforts underway in that area as well. But if we think about, if we can frame the question, is this the right problem to be attacking? The development of liquid fuels by CO2 reduction. And we can see one way to think about this is in terms of the volume of production of carbon in gigatons per year and the assignable economic value associated with that carbon. And we can look, for example, at the sequestration of carbon, which essentially is it's a cost. We can't, aside from processes such as enhanced oil recovery, that represents a pure cost. We can see also, for example, that the cost of coal is very, very low, and that's going to be a big challenge. And so we may need policymakers to incentivize us to work with fuels and keep solid hydrocarbons like coal sequestered as much as we can. But what we can see here is that gaseous and liquid hydrocarbons particularly represent a very interesting balance between the volume of use and the volume of emissions of carbon and economic value. For example, just as a sort of cost benchmark, we can think about the recoverable economic value associated with liquid fuels being comparable to what is the current estimated cost of carbon capture directly from the air. And of course, in order to close the fuel cycle completely, we have to reduce the cost of this dramatically so that we can develop not only capture but also electrochemical processes that could allow us to defer the emissions of carbon in these forms. But we can see, of course, that many specialty and commodity chemicals, polymers and other chemicals, have higher value but lower volume. So this looks like a very attractive target for solving many of our challenges associated with carbon emissions. And so if we think about the fuel products, of course, when we think about CO2 reduction, unlike water splitting, we have more than one product. We have more than just hydrogen as a possible focus. So we can think about both the use challenges and also the energy density associated with this in terms of the energy per weight, the higher heating value. And we can see that gaseous hydrocarbons have quite attractive higher heating values and have the advantage that they can be separated easily from liquid electrolytes and can be compressed. Alcohols such as methanol and ethanol represent attractive targets also from the point of view of higher heating value. It does involve a step including separation of from water electrolytes, and for which there are commercial processes available, and then also of liquid hydrocarbons. So if we look at hydrogen, of course, which has been our objective over the last 5 years, is a fantastic candidate in terms of its energy density, but has, relative to liquid fuels, relatively greater challenges in the storage and transportation of hydrogen. I would note here, if we look at carbon monoxide, that's of course one of the first products of CO2 reduction, and we can think about carbon monoxide as a benchmark to compare against these other products, and although this is the initial product we can see of CO2 reduction, we see that carbon monoxide will not be a primary product for JCAP, which aspires to focus on reduction of CO2 as a final end product to liquid or gaseous hydrocarbons that are noted above. And so the focus is in renewal of JCAP is on developing scalable technologies that convert CO2 directly to liquid transportation fuels or gaseous transportation fuels under mild conditions with only solar added energy. Of course, we have thermochemical routes such as Fischer-Tropsch and using water gas shift and reverse water gas shift together with hydrogen generation. We have routes that are available today to, in principle, make liquid fuels. And JCAP will be exploring electrochemical approaches to CO2 reduction that can operate on a competitive basis with that. And so its project structure is going to be configured to address this challenge and focus on electrocatalysis for CO2 reduction, photocatalysis and light capture, materials integration, and the modeling and prototyping activities that have allowed us to define the characteristics for water splitting solar fuels generator focused on the problem of a integrated CO2 solar fuels generator, but really with an initial focus on the component elements there, membrane electrode assemblies and so forth. So I want to just spend a few moments now and talk to you about accelerated materials discovery. We have urgent challenges associated with electrochemical transformations of CO2, so the accelerated materials discovery is a really attractive path, and I want to describe a combined experiment and theory team. Here's the team, Chimanyan, Guo Li, and Ji Yu, who are supervised by theorists Jeff Neaton and Christine Persson and John Gregoire, an experimentalist. And the focus is really on development of new stable photoelectrocatalyst materials. And of course, in seeking this holy grail for photoelectrochemical solar fuels generation, we seek semiconductors that have band gaps between 1 and 2 electron volts, so they're broadly absorbing the solar spectrum, and valence and conduction bands that straddle the water oxidation and water reduction levels. So we know about many of the choices that are available to us that have these characteristics, and in general we don't have a large portfolio of ideal candidates here. We have many that are stable against oxidation and under oxidation and reduction conditions, and have aligned band edges but have band gaps that are often too wide, or others that don't have the proper band alignments. So the team, the high throughput team, began thinking about this enterprise starting with a large pool of candidates of chromium, manganese, and vanadium-based ternary oxides. And the first theoretical and computational approach using PB plus U first principles theory focused on understanding the phase stability, and that yielded a couple of thousand candidates from this ternary oxide base, and a second screen of calculations looked at using hybrid density functional theory focused on finding materials with the proper band gaps, and A third stage focused on understanding and computing the band edges and understanding the stability in water, including some very interesting work on computational mapping of pore bay diagrams to understand the electrochemical stability. And then finally, generation of some selected candidates. And so this stability assessment with the pore bay diagrams yields a large number of potential candidates from which we can now select materials that have proper alignment of the conduction and valence band energies. And among these, two candidates stood out, which were manganese nickel oxide and manganese vanadium oxide, manganese vanidate. And pursuing further the work on the manganese nickel oxide and manganese vanadium oxide, we found that the manganese vanadium oxide exhibited stability under electrochemical operating conditions for OER catalyst and for photoanode electrolytes. And the high throughput experimentation team swung into action to look at the generation of using combinatorial synthesis methods of a whole range of possible ternary alloys, including component elements manganese, vanadium, bismuth, cerium, and zeroed in on the bismuth, the manganese vanidate class. And the theoretical team was able to, using the hybrid density functional theory approaches, find that the manganese vanidate phase, this high temperature structure of manganese vanidate exhibited an attractive band gap and nearly optimal band edges for water splitting. So the experimental team zeroed in on manganese vanidate phases as and found that and identified a number of candidate compounds, and in fact there was very, very good experimental and theory comparison between the stable phases at a given composition in both theory and experiment. And the theorists identified this manganese vanidate phase as a stable small band gap light absorber with a band gap of 1.8 eV, and very shortly thereafter the experimental team was able to identify and show that this band gap could be validated. And in high throughput experimentation, they were able to directly and immediately see photocurrent from photoanodes with a co-catalyst. And this whole effort took place in the course of a number of weeks rather than usual materials development time cycle spanning from months to years. And so among all of these criteria for having a good light absorber with an optimal band gap and favorable band alignment and photoelectrochemical stability, manganese vanidate looks like an interesting case. And there are, of course, many others in these ternary alloy compositions of vanadium oxides that are potentially also other attractive components to pursue, and that's underway. So I want to spend just a little bit of time saying something about the approach that JCAP is taking in addressing the considerable challenge of heterogeneous catalysis for CO2 reduction. And the approach in general across all of the efforts is to use a theory-guided approach to screen new catalysts and to identify descriptors for CO2 reduction and to compute the energy landscapes with both the thermodynamic states and also kinetic barriers, and to rapidly synthesize and screen these using large area electrochemical cells that can detect the full range of products for CO2 reduction. And of course, one of the big challenges, as we know from extensive previous effort in CO2 reduction, is the fact that while we have CO2 reduction catalysts that are active and stable, it's very difficult to make them be selective, heterogeneous catalysts that are selective. So what we need to do is to break scaling, so-called scaling, in which the activity for generation of one product can be regulated and tuned relative to that for another. And so to address this, JCAP has significantly expanded its range of theoretical efforts, including first principles theory of both the thermodynamic and kinetic landscapes, the highly resolved theory of excited states, and also theory of the landscape that includes a detailed treatment of electrolytes, the solid electrolyte interface, and functional components on the CO2 reduction cathode. The work on the theory side is complemented by some very powerful capabilities using Operando characterization of CO2 reduction. And as an example, the Operando characterization can see chemical transformations on the surface under operating conditions, which is a very important, as we have seen in a number of examples to date, both chemical transformations of the surface and structural transformations. And so as an example of the structural transformation, in situ electrochemical STM is able, which is work being done by John Heminger and Manny Soriaga, has been able to detect, for example, on copper, which is one of the most widely studied heterogeneous catalysts for CO2 reduction, a remarkable transformation where polycrystalline copper surfaces under electrochemically active conditions for CO2 reduction undergo nanoscale transitions to faceted 111 and then 100 surfaces. And this actually broadly helps us to understand what has been noted in the literature previously, that the chemical activity for CO2 reduction of polycrystalline copper was very much like that of 100 copper. And indeed, we can see that's because under electrochemical operating conditions at room temperature, the surface transforms on the nanoscale to locally 100-like structures. And I think this is just the tip of the iceberg, so to speak, on understanding in detail the nanoscale and under operating conditions, the complexity of CO2 reduction. Okay, so just what I'll do is now note that we've, over the first phase of JCAP, we've developed, using an integrated approach, prototypes which give blueprints for stable, greater than 10% water splitting devices. And a hallmark of JCAP has been an accelerated materials discovery effort combining both theory and experiment. I showed you an example which led to the rapid identification of manganese vanidate as a potentially stable and electrochemically stable and high photocurrent light absorber material. And I described briefly some of the work that's underway on heterogeneous catalysis for CO2 reduction. So thanks very much, and we'll be happy to field any questions.
Thanks for the overview, Larry. I have two quick questions. As you well know, the reaction fluxes of CO2 reduction are limited by the poor solubility of CO2.
That's right.
Relative to water. Water.
That's right.
Molar. So could you tell us what JCAP scientists are doing to get around this?
Yeah, well, so we tend to, we're developing an approach to CO2 reduction that views the heterogeneous catalysis as being a a sort of in an electrolyte as being one that demands a functionalized photocathode in which, for example, bringing together polymer membranes or metal organic frameworks, we may be able to pre-concentrate CO2 in the vicinity of the heterogeneous catalysts. As you know, there are many big challenges. For example, in aqueous electrolytes, very often CO2 reduction loses the competition with respect to hydrogen generation. We have, of course, issues with solubility. We have issues with stability of carbonate and bicarbonate ions in solution. But we think that by functionalizing and developing sort of a heterostructure electrocathode, we may be able to break some of the breakthrough on some of the challenges that have limited the electrocatalysis in the past.
My second question relates to the poor carrier mobilities in complex oxides like the ones you talked about. Again, is there a way around that?
So I guess what I would say is that in terms of photoelectrodes, JCAP has taken a dual approach, which I essentially was made evident by implication in my talk, which is first to work with well-known high-performance photovoltaic semiconductors that are not stable in the electrolytes required for solar fuels generators, but to protect them, and Matt McDowell will talk about that shortly. The second is to develop inherently stable materials. And so this combined approach of high throughput experimentation and theory can identify the compounds, but of course in order to get to the point where we can validate that the mobilities are as high as the theory predicts them to be requires considerable more directed experimental effort on crystal growth and so forth. But at least we can begin to identify some new candidates of materials that have in principle the right characteristics if we can make them using more directed material synthesis techniques.
Does this approach look more attractive in your opinion, for example, using photoelectrochemistry to produce hydrogen and go on to reversible gas?
Right, okay. Yeah. Okay. No, you're right. So that's a very good question. So for all of those who didn't hear it, the question is, so how about electrochemical transformations versus a Fischer-Tropsch or reverse water gas shift approach? Yeah. So thermochemical approaches. So we're actually doing a sort of benchmarking study looking at the characteristics both in terms of the energy return on invested and also the essentially the techno-economic approach for systems that involve thermochemical and say starting with renewable hydrogen. So for example, from a solar fuels generator for water splitting versus a solar fuels generator that would directly electrochemically reduce CO2. And so we're working on this to define the operating characteristics, in other words, the efficiency and Faradaic yields for product that would be required to generate a sort of fair competition between those two approaches. So I won't tell you all about the details here, but I can just tell you that that gives a useful benchmark, and you can sort of think about these as allowing, because of course we have thermochemical routes to generation of syngas, and then from syngas to methanol, methanol to gasoline, and so forth. So you can compare a direct methanol to as a route to liquid fuels with a thermochemical approach. And so that defines the device efficiency that we're looking for here ultimately. Yeah.
Also, can you comment on the different type of catalysis you use in CO2 reduction between going to hydrocarbons, which is typically what you get with a copper-based catalyst, and making alcohols separated from the electrolytes?
Yeah, so I wanted to, I didn't get a chance here in this brief overview to tell you about the diversity of approaches that we're taking on heterogeneous catalysis, but not, certainly they go well beyond copper. I just wanted to note some of the, even for something as simple as copper, some of the things that are being revealed in the recent past about, but we're looking at a variety of both metals, metal oxides, nitrides, and semiconductors, which may have an approach that would enable us to suppress hydrogen evolution, for example, relative to CO2 reduction. So there's a diverse, and you'll be hearing more as the program develops about the different approaches, but there's a wide variety of catalysts being studied, and we are not, I would say, we're not fixated on a single fuel product as an objective. And I think at this point the work on CO2 reduction is a scientific enterprise that needs to encompass a broad range of approaches and possible fuel products, but we're trying to sort of develop analysis that can circumscribe the ones that look attractive versus the ones that don't. Yeah.
So in one of your slides, it seems like your target is CO2 reduction from ambient air. So, but there's a 20% oxygen in the air. Can you comment on this negative effect of oxygen if you use ambient air? Because it may significantly improve the backward reaction. So oxygen is present.
Right. Okay. So I guess so the question was about the ambient for CO2 reduction air, and I should say that the scientific focus at the moment is on CO2 reduction using concentrated sources, so those concentrated sources, for example, if you were to look at concentrated sources from flue gas, we'd be looking at, but of course, ambient air represents a huge challenge because of the dilute concentration of CO2 in the air. There's a huge thermodynamic challenge there. So, but the scientific focus of the heterogeneous catalysis is really on looking at catalytic processes over that range of partial pressures, but the initial focus will be very much on concentrated CO2, just to understand reaction mechanisms. Okay, so I think what we should do now is to transition to our next presentation, which will be given by Matt McDowell, and he will tell us about work on the protective coatings that have enabled some of the advances in solar fuels generators that I described in the overview. I have to find it here. And I should just mention that Matt is recently has graduated, so to speak, from JCAP and is now moving on to life as an academic, as an assistant professor, and will describe some of the work that he did during his term as a postdoc in JCAP.